Hi, everybody. Well, it's taken a few weeks to get here, like 11 of them, but we're at the end. This is the end of Chem 140, and all that's really left to do is what we're going to do today, which is sort of already on the screen right there. And then that's it. That's all the content. So this is the last lecture. What other things are going on? So let's see here. We've got a quiz that was due yesterday. Tonight is the last call. Make sure you get that in by the deadline. That's quiz number 8. There is an exam this week on Friday. You can request to have the day moved forward or backward if you'd like. I just need an email. I haven't addressed any of the emails I've gotten asking about that just yet, because I'm going to do that after class. So if you have sent an email about that, don't worry about it just at the moment. There's also a cat. Hi, say hi. And she's gonna harass me until I let her say hi. So here you go. Say hi. Say hi. Meow. What? What? I swear, she just wants to rub against the microphone. Hi, I'm a cat. Rub, rub, rub against everything. Huh? Okay, you gotta go somewhere else now. We're not doing this like you did yesterday. No, this is not you going somewhere else. This is you coming back. She's gonna jump right back up on the chair. I put her on the ground. I don't have my tablet. I need to get that. So yesterday we talked about molarity. Molarity is the comparison of the amount of stuff per unit volume. And I drew a few pictures for you. And then we expressed it using this formula. And we did a very basic calculation where we put the number of moles of this calcium chloride divided by the volume of the solution that we made. And then we gave a molarity. Now, it's important to note that this ratio is per liter. If I can get the pen out here, there we go. So this is per liter. Which means that there are that many moles in 1 liter. And if you want fewer moles, then you would take less than a liter. And if you want more moles, you take more than a liter. It's just that the concentration tells you how much you get per 1 liter. Kind of like how many grams you get per cubic centimeter of a solid when we look at density. If you want more mass, take a bigger volume. If you want more moles, take a bigger volume of concentrated solution. I gotta find the chat log. All my windows are buried right now, so there we go. Alright, so with this in mind, we can take this expression right here. Oops, it didn't actually draw. And we can actually rearrange it a little bit to give us something that's useful. And we're going to see this on a slide that's coming up. And the thing that we're going to do, so molarity I'm going to write as a capital M. This will be moles, and then volume will be V. And what I'm going to do is I'm going to move the V to the other side there. And we get this expression. Molarity times volume equals moles. So if you need to know a certain amount of solution, or a certain amount of moles, or a certain whatever you need to do, you could solve for one of these knowing the other two. Now, when we prepare solutions, generally speaking, we're going to elect these two to be whatever we want them to be. I want 1 mole per liter. I want 5 liters of it. And then you would times them together and figure out how many moles you need to weigh out to make the solution. We're going to show how to do that today. So let's suppose that I want to make this solution. I want to make a 1 molar NaCl solution because I'm trying to mimic, say, I don't know, a saline solution. No, not saline, because that'd be way less concentrated. I'm trying to mimic, say, like the ocean or something. I want a solution that is as salty as maybe some part of Puget Sound or whatever. And I want to make this solution in the laboratory. How do I do it? Well, the first thing that we need to do is figure out how much NaCl we would measure out. And we have to figure out its mass because it's a solid. So what do we do here? Let's do this. I'm hitting the wrong button. There we go. All right, so I have this expression, molarity, capital M, equals moles of solute over volume of solution, which I can rearrange to get that. Now, according to my solution, I want to have 1 mole of NaCl per liter, because I want a 1 molar solution. I should probably make this look better. Times the volume that I want to make, which is 1 liter. And then I'll just cancel the units out that are able to do so. So that's the volume. And you'll notice I'm left with moles, which is why this equals moles. Now, 1 times 1 is 1. So that's not very exciting. But this is the number of moles that are in that sample. Now, what I need to do is I got to turn that into a mass, right? Well, how do I do that? I can turn moles into grams. We've been doing that all through units 12 and 13 and 14 and 15, right? I just go over to Lentech and figure out what the mass of grams per mole is of NaCl. And so I got to go find Lentech. Let's window capture that one. There we go. So there's Lentech. And we will just NaCl. And I got 58.44 grams per mole. And so I would weigh out this much NaCl. 3 sig figs because the number I started with has 3 sig figs. So I will put 58.4 grams of NaCl onto like a weighing boat or something like that and weigh it out. And where will it end up? It will end up in a flask. Now, if we were in a laboratory, I would be showing you how to do this in front of you. But unfortunately, we're doing this online, so I have to basically draw pictures. And we'll have to refer to that. So here's what you do. So the first step is we're going to weigh out and add the amount of NaCl that we calculated. And so that was this right here, 58.44 grams. We're going to put that in this container. And you could see that I have it in like a graduated cylinder. And it's getting poured in there. Now, odds are I'm not going to be able to get every last speck of salt. There's going to be like a little bit of powder along the sides of the container and this funnel here. It won't all make it down here. And that would introduce error if I didn't get it in there, right? So step 2 is to add water. And your water, not only should the water just go into the container, but the water should also rinse up into this guy too. So rinse well. And the reason for that is because, again, there might be sodium chloride powder or residue left in the containers that it was handled with. And you want to make sure that you get all that because it's part of the mass that you weighed out. So you want to rinse it really well with water and make sure that it all goes into the container. And you're going to add enough water so that it goes to wherever this little mark is on the container. There's a line on our flask that indicates the volume that we've chosen. This type of flask is called a volumetric flask. And what a volumetric flask is it's just a flask that has a very fixed volume that is known to many sig figs. We have specifically made it so that there is very little error and that the container has a well-known volume. It's no good for any other volume. So this specific one that we're looking at is a 1 liter volumetric flask. We could get a 500 milliliter flask. We could get a 250 milliliter flask. There's all sorts of different volumetric flasks out there. All right. Once you have added all the water into the container and you've added it to the line, the last thing that you want to do is mix the solution really, really well. And it turns out that that's very important because in order for it to be a solution, it has to be homogeneous, right? Well, if all the salt is at the bottom and it is just dissolved, then it's not going to be completely homogeneous. The water up at the top here will have less sodium chloride in it than the water at the bottom here, by virtue of it just takes it longer for the sodium chloride to meander up that column up in that direction. But if you mix it roughly 50 times, so put the cap on it and invert it 50 times or so, you will get a well-mixed solution. And this is actually extremely crucial to do. This is the part where people screw up. They don't mix the solution well enough, and then when they start using it for experiments, they're not all the same concentration because the stuff at the top is more dilute than the stuff at the bottom. So it's very important to mix well. So I have described how to make a solution in 3 steps here. The first step is to weigh out the correct amount. The second step is to add water until you reach the mark. And then the third step is to mix extremely well. There is a secret 4th step. Enjoy. All right, so what I want you to do is I want you to follow these same 3 steps, or 4 if you want to enjoy, to make this solution. I want you to make KBr. And I want you to make a 3.50 molar solution of that. And I want 1 liter of it when you're done. So what I want you to do first is calculate how much KBr you need to put in the flask. Tell me that in grams to the correct number of sig figs. And then describing it in words or pictures. Obviously, you'd use words because you can't upload pictures into the chat. It won't show up on the log. How did you make the solution? And your answer should be 3 steps. Step 1 is how much did you weigh out? What do you do with it? Do you throw it on the floor? Do you toss it in the ocean? What do you do? Step 2, what do you do there? Step 3, etc. So give me the 3 steps that we just talked about. Type your answers in the chat when you are all set, and we will go over the results in just a bit. Now, you're not supposed to drink your solution. You're just supposed to enjoy. Enjoy the fact that you've made it. I guess students in the past likened this procedure to like bartending. And so they said, well, what, you don't get to enjoy what you made at the end? And so I was like, oh, okay, well, step 4, enjoy. There you go. All right, I'll be back in a little bit. About 4 minutes or so to do this on your own, and we'll go over the answer. All right, 1 or 2 more minutes, and we'll go over the answer. All right, let me just take a drink of my water here. Oh, man, I need to drink something other than carbonated water. Even regular water feels so pedestrian to me now. Which is a dumb way to think about water, but... Alright. Alright, so I want to make this solution here. I want to make a 3.50 moles per liter KBr solution. And I want to have 1 liter of it. So to figure out the number of moles, remember that molarity equals moles over volume. And that if I rearrange, I get m times v equals moles. And so that would be 3.50 moles per liter times the volume gives me 3.50 moles of KBr. Okay, well, if we've got that, we can then turn that into a mass. And you could do that. You could just keep the calculation going. I ran out of space, though, so I was just going to set it up to do it this way. So we'll turn moles of KBr into grams of KBr. And so we got to go to Lentech for that, too. So let's see here. Make sure that we got that. Boop, there we go. So there's my Lentech on the screen there. And I want KBr, 119 grams per mole of KBr. So boop, we'll get rid of that. And we'll write it down here. 119.00 grams per mole. And I believe 417 is the number that I get, because I do these problems enough with students that I just have the numbers sort of stuck in my head. Yeah, 417. So there's our solution. Oh, the cat has taken up residence on the chair, and now I just have to reach over and pet her. Oh gosh, don't do that. I can't. She's sitting there going, because she's happy. I want her to be quiet so I don't get distracted. Alright, so that's how many grams of KBr we have. So now we need to make the solution. So step 1 would be to add the KBr that we weighed out to a flask that has the volume that we want. And so the volume that we want is this volume. And again, this number that we got here in the previous, so this number right here is this number. Well, once we've done that, you can add the H2O to the fill line or the fill mark. And then you just have to mix it really well. And then, of course, enjoy. There you go. So that's how you make a flask. Or not a flask. That's how you make a solution in a flask. Yeah, don't drink. Just enjoy. Visually enjoy. All right. You could do this process for any solid substance. So you can add your solid to the container in this manner and then prepare the solution following this procedure. Any questions, let me know. Now, the next thing that we are going to do is we're going to prepare a solution where instead of having a solid, you have a liquid. And so this is known as dilution. Now, in order to do dilutions, we need to know how many moles are in the sample that we start with so that we know how many moles there will be present when we finish. And so that's where this slide comes in. It talks about volumes and molarities. So we know that M times V, capital M times V, is moles. So if you have any sample, you can solve this equation. There is an important constraint, though, that we might have taken for granted up to this point. And that constraint is that the volume must be in liters because of how the units work out. So if I multiply molarity, and then I have a volume that is not in liters, nothing cancels and I don't end up with moles, right? So that won't work. What I need to do instead is put it in liters, and then everything does work, okay? So be mindful of that. If you're given a volume in something that is not liters, and oftentimes you are, because a liter is kind of a cumbersome amount of liquid to work with, then you need to convert it to liters. Now, I think the workbook is going to give you really obnoxious volumes like gallons or like maybe even cubic feet or other bullshit units like that, because Samita loves her bullshit units. Because the whole point of Chem 140 is to make you practice doing conversions over and over and over, and the best way to do that is bullshit units. You know, units that you aren't going to ever possibly use, like how many pounds of sugar contains how many atoms or whatever. And those are good problems. Like, that's not practical. We're never going to do that in real life, but they're good for exercises. And so that's what we're going to make you do. All right, so let's solve this problem here. So if I have 500 milliliters, I don't need to do the conversion for you at this point. Oops, I only need 3 sig figs, though. Boop, there we go. So you should know by now how to convert 500 milliliters to liters by multiplying by 1 times 10 to the minus 3. Oh, I've subbed for Samita's class and given her problems out, and I'm like, wow, her problems are so much harder than mine. Which isn't a fault on her. I should step up my game and give you guys crazier problems, but I haven't. All right. So we have this many milliliters and this many moles per liter. So if I want to know the number of moles, oops, there's my molarity times the volume, which again has to be in liters. Otherwise, you can't cancel these out. And so when I multiply those two things together, I should, if I'm doing my mental math correctly, you should get this number, 0.175 moles of magnesium hydroxide. And now what you could do is you could turn that into grams or whatever application you need to do. Oops, let me clear the text out of the way. All right. Oh, I have more practice exercises for you. Okay, cool. So we're going to do these practice exercises before we go on to the dilution. We'll do that after this. But just to get you to do more calculations and more exercises with these numbers and these units, here's 2 problems that I have for you. So the first one is a 35 milliliter beaker contains 2.50 molar HCl. How many moles of HCl are in the beaker and how many grams of HCl are in the beaker? So you can figure that out. You will need to use Lentech. And then down here, I have a 250.0 milliliter solution of 3 molar potassium dichromate. And so what I want you to do first is find the mass of the potassium dichromate that was used to make the sample. So in other words, you're going to do that dilution calculation backward. And then as a practice exercise to remember how to do stuff from Unit 13, or not Unit 13, Unit 12, actually, I want you to tell me the mass of just the chromium. So there are 2 ways to do that. You can either do stoichiometry, where you say, okay, in 1 mole of potassium dichromate, there's 2 moles of chromate, and then turn it into a mass. Or you could figure out a percent mass, and then times that by the mass of potassium dichromate that you calculate in part 1. Whichever way you want to do, either way works. So go ahead and try those. I'm going to give you about 6 or 7 minutes to do that. We'll go over the answers, and then we'll dilute solutions. And then we'll take a break. So I'll see you in a little bit. Type your answers in the chat as you get them. How are we doing? Type any answers you got in the chat. We'll go over the answers in about 2 or 3 minutes. All right, 1 more minute. We'll go over the answers together. All right, let's solve these problems. So first I want to do this, and we'll just do that. Yeah, let's clear everything real quick. Pen, there we are. All right, so I have a 35 milliliter sample of 2.50 moles per liter, or moles of HCl per liter. And so I need to convert this to liters, like that. And again, you should know how to convert from milliliters to liters by now. And then we would use m times v equals moles. And you've already seen me derive that enough, so that should be okay. So we'll just multiply these two things together. So I've got molarity, which is this, 2.50 moles HCl per liter, times the volume in liters. And when I do that, that's not a calculator, that's my phone. Times 0.0350, 0.0875 moles of HCl, which is the answer to the first one. Oops, I'm sorry, I didn't mean to do that. And then for the second problem, we'll just turn moles of HCl into grams of HCl, which we've been doing all along. And so we'll go to Lentech. I won't put Lentech on the screen because you could type HCl in yourself. You should get 36.46 for that. So 36.46 grams per mole. And so that number times 0.0875, 3.19 grams. So, yeah, the only issue that you had there, Kyle, was that you must have used milliliters in your calculation because your answers were 1,000 times too big. But otherwise, it was done correctly, so good job. All right. And William and I got the same answers, so that's good too. Hooray. All right, so that's the first one. Let's do the second one real quick. So, oh, I got to go over here and do that first. So we'll put this. Whoop, there we go. It's the magic of post-production stuff. I can just do whatever I want over here. All right, so now for the next problem, I'll just change color here. I'll have 250 milliliters of solution, and the solution that I have is not 30, is 3.00 molar K2CR2O7. So first things first, we'll just turn the volume to liters. And then we can figure out the mass of the potassium chromate by multiplying m times v equals moles. And so we'll punch that in. So 3 times 0.25 is 0.75? Yeah. So there's that. And then we'll multiply that by the number of grams per mole. That's not what I meant to write. All right, so that will give me the number of grams. This one I have to go to Lentech for because I don't know it off the top of my head. K2CR207. 294.18 grams per mole. And so when I multiply those two together, I get 220.6, which becomes 221 grams of potassium dichromate were used to make the sample. So if I wanted to prepare this solution, I would weigh out 221 grams of potassium dichromate in a weighing boat, put it in the 250 milliliter beaker or volumetric flask or whatever, and then add enough water. That's a lot of mass. 221 grams is a lot. I remember when I made solutions of things that were heavy, like they had lead in them or whatever, and you're weighing out like 500 grams, and it's going in this like teeny tiny container, and it's like, how the heck is that all going to get in there? And it dissolves in. It's kind of amazing that it does. And then finally, what's the mass of only the chromium atoms? Well, if I take this number right here, and I say, well, I know how many moles of chromium, or of the big thing I have, I could say remember doing this? I could say in one of these, there are 2 of those, right? Because of this number right here. So using the coefficients, and then I just have to turn moles of chromium into grams of chromium. And that's on the periodic table. I just got to find it. It's under a video game controller here. 51.996. Grams per mole. And so that should be the mass of chromium in the sample. And I get 77.9, or 78.0, actually. Grams of chromium. Now, this makes sense because this number should be less than this number that we got up here, right? So if you got a number that was greater than 221, you can't have more chromium than the mass of the entire sample, right? So this is how I would calculate it. The other way that you could calculate it is you could find out what percentage of chromium this is, and then multiply by that. And you could, of course, go to Lentech to do that. According to Lentech, K2CR207 is 35.35% chromium. So 221 times that percentage should be 78. And just doing the mental math real quick, it seems like it would come out to be. Either of those answers is fine, or either of those methods, I should say. All right, so we're going to take a short break here. Let me get the, let's see here, break time on the screen. We'll get the timer going. Boop. Boop. No, I do not want to update the timer. Stop asking. All right, I'll start this up. We'll get the Outer Wilds music playing again. Outer Wilds is such a good game. You should play it. And I'll see you in a little bit. So I didn't actually time that. That the music sort of just did that on its own. And I was like, wow, that worked out really good. Anyone who's played Outer Wilds knows what that music means. Um, Outer Wilds is a game that I can't say anything about because anything is a spoiler. If you know nothing about it, you are the perfect person to play Outer Wilds. What I can say is it is a space exploration type mystery game, where everything is just puzzles, and not like puzzles and like move the blocks around and then fit them into a thing. It's like actual like problems that are going on, and you have to engineer a way to figure out how to fix them. Like, how do I get into this ocean before the current takes me away, or how do I navigate this system of caves or whatever, stuff like that. So excuse me. I definitely recommend it to people who especially if you're doing like anything space related. Like, it's very good. But it's a very good sort of critical thinking game, and dealing with information and acquiring that information, and then how do you apply it. So all right, so we have learned that we can do this sort of calculation very easily. So I'm going to skip this slide because we've done a ton of this. I don't know why the slides go in this order. We've done plenty of this. Let's just talk about dilutions. We could do those extra problems tomorrow if we want on the during the Q&A. All right, so what we're going to do now is we have learned how to make solutions out of solid components. You weigh out this amount of solid, you put it in the beaker, or the volumetric flask, actually. You fill it with water, and then you enjoy. Mix, of course. What if your solution is already a solution? Like, I already have, like, a molarity. I just want to have less molarity. I want to dilute it. Well, here's what you do. Remember that you can dilute any solution by just adding water to it. You turn concentrated ones into dilute ones. Now, how do you do that? There is a formula that I have here on the screen, and it's called the dilution formula. And the reason that this is called the dilution formula is because we only use it for dilutions. Okay? Be very careful, because this formula looks kind of like other things, and then later on you're going to want to apply it everywhere, but don't. The dilution formula is only used for dilution, so you're only going to use it for this practice. Now, what does this actually turn into? Remember that m times v equals moles, right? So we have moles, and then we have S, whatever S is. We'll talk about that in a second. Equals moles, not mold. I wrote the D too early. But moles, if I could touch the button, come on. There we go. Moles dilute. Now, what does S mean? S is your stock solution. Or in other words, what's in the stockroom? This is the concentrated solution that we have in the stockroom. We keep this so that we can make other solutions from it. What about D? D is the diluted solution. And it's the one that you are making. And then M is a molarity and V is a volume, right? So in other words, what this equation is saying here is that the number of moles that you use from the stock solution will be the number of moles in the dilute solution. And that makes sense, right? Because if this is what I take beforehand, here's my stock solution, and here's my concentration. There's a lot of it. And of course, PowerPoint is freaking out here. Afterward, when I make my solution and it's in a bigger volume, I'm going to have the same concentration. Or not concentration, I'm sorry. I'm going to have the same number of moles, but the concentration will be less because the volume increased, right? So the moles are just my dots in those pictures there. And that represents the stuff that I've brought along. The amount of stuff I have before and after I dilute is the same. What changes is the volume. And if the volume goes up, the molarity goes down as a result. Because remember, molarity is moles per liter. So molarity, moles per liter. And if this number increases, then this number must go down in order for this number to remain the same. Wait a sec. I'm sorry. I've totally screwed up this explanation here. I wrote the wrong thing. Okay, pretend I didn't say that. What I meant to say was that if this number stays equal, and this number down here increases, then this goes down as a result. I wrote the wrong thing in the wrong spot. All right, so that's what the formula means. Let's do some applications with the formula. So again, M is stock and D is dilute. M is a molarity and V is a volume. In the problems that you're going to be given, you're going to have to identify what all the numbers mean. And so you're going to get a problem like this. And your job is to figure out, okay, well, if this is my formula, where do all the numbers go? And so that's going to require some critical thinking. You're going to look at the numbers in the context of the problem and then identify what they are. So if I write all these down, I can assign them based on what the context is. So I have this concentration in the stockroom. So it's a concentration, so it has to be an M. And I wrote the word stockroom, so this is going to be this. Then my next move would be, okay, I'm going to look for the other concentration. So that would be this. And now I got to look for volumes. I want to make 3 liters of this. This is the dilute solution. So that must be the volume of the dilute solution. Which means that this is going to be the number I solve for in my expression. Now, I've wrote these out as a list. What I tend to do is I tend to do something like this. I make a little table. So this would be MS, which would be 10 molar calcium chloride. This would be the dilute. This is what I'm solving for. There you go. So whichever method of organizing the information helps you. I like to make the little table, but you can also make a list. And so you're going to see me making these tables. Just I'm writing it out as a list first so that you can see that when I translate it to this table for future stuff. All right, so now let's go over here. We'll just put this table in here. This will be okay. And so I want to make a solution out of all of this stuff. And what I need to know is, what the heck do I do with this information? Well, if D is the diluted solution that I want to make, then here's what I'll do. I'm going to rearrange my expression and solve for the thing that I don't have, which is that. So I'm going to divide both sides by m sub s. And then I'm going to calculate this result by plugging in all these numbers. So I've got m sub d is 0.500 moles per liter. V sub d is 3 liters. And then m sub s is 10 moles per liter. You will notice that I just reading at capital M, and the reason that I'm doing that is because they cancel. And so when I do this calculation, I should get this, it looks like. 3 times 0.5 is 1.5. 1.5 divided by 10 is 0.15. Yeah, that looks good. I mean, I have a calculator right here. I guess I could type it in. Yeah, I got that. Okay. So if I do this calculation, I get this. This is the volume of stock solution that is needed. So this is what is needed to prepare the diluted solution. Because what we did was we figured out how many moles were needed in the final solution to be prepared. But the starting solution, I can take as much as I want, and based on its molarity, I can adjust for how many moles I will need in the end result, however much that ends up being. So we do the calculation in this way to figure out, okay, what volume would contain that number of moles that I need for the solution that I want to prepare. And once I figure that out, we can now prepare this solution. And we're going to do this in a method that is similar to how we did it with a solid solution. So the first step that we're going to do is we're going to measure the volume of the stock solution. And I'm going to indicate what that solution was. It was a 10 molar calcium chloride solution. And then we're going to add it to the volumetric flask. So that's step one. And then step two is just to fill to the mark with water. And then step three is just mix really well. And of course, enjoy. So same strategy as with the solid reagent. This time we just have a liquid. We need to figure out how much liquid of the stock solution is necessary. So let's see that in pictures, because that's what's going to pop up on this screen right here. Once I hit clear. There we go. So here's my... Oh, well, there's our answer that we got. There's our picture. So I'm going to measure out the amount of stock solution that I calculated, which is this number right here. Let me get the pen back here. So that's this. And then... So there's my step one. So then step two is to dilute with water by... Wow, what on earth? It's like the polling rate on this on PowerPoint is just complete garbo. Okay, I'm apparently writing like a robot today. That's fine. Anyway, you want to also add in all the water that you... Oh, for fuck's sake. I'm convinced that Windows is just complete shit. Utter rubbish. Remember that you want to also put the water into the container that you are pouring from because you want to make sure that you get it all. And then rinse out the funnel too to make sure it all gets in your container. Once it's in the container, you're going to, of course, mix well. Now it's working fine. I don't understand. And then enjoy. Try to enjoy if you can under these working conditions, because for fuck's sake. All right. So that's how we make solutions. So let's go ahead and do another example here. So I'm going to give you stock HCl. This is concentrated 14 moles per liter. This is generally speaking way more concentrated than you need for virtually any application. Like if you were working in industry, you might work with 14 molar HCl. But in the laboratory, there's no need for it. I want to make 1 molar HCl, which is 10 times more concentrated than your stomach acid. And stomach acid is quite concentrated, right? So how do I make 1 molar HCl out of 14 molar HCl? So use the formula MSVS equals MdVd to prepare the amount of stock volume that you need to take to make the solution. You're going to notice that you're always going to be solving for the volume of the stock solution in these prep problems. Now, there are other problems out there that may ask you to solve for other things, but generally speaking, if it's a how do you prepare the solution, you're 99% of the time you're going to want to solve for the volume of the stock solution. So go ahead and try this. I'll give you 5 minutes to look at it and tell me what volume you need of stock solution to make it. And then, again, in the procedure, write in your words how you'd make the solution. All right, I'll check back with you in just a little bit. About 2 more minutes, we'll go over the answer. All right, let's go over the solution to this. Oops, I didn't capture anything. All right, so there we go. There's my answer. Or not my answer, my problem up there. And I want to make this solution. How do I do that? So I first need to write down my little grid here. And I need to identify what parts I have. So the stock room has 14 molar HCl. So the molarity of the stock solution would be 14 moles per liter. And I want to make a diluted solution of 1 mole per liter. And I want 1 liter of it. So I need to solve for this part. And there's our formula. So I'm going to solve for the part that we need to. And so I'll punch in all the numbers here. So MD was 1 mole per liter. V sub D was 1.00 liters. And, oops, I'm going to run out of space. The stock molarity was 14 moles per liter. And so I get 0.0714 liters. I messed that up. Hold on. There we go. Now, if it helps you to conceptualize this to put it into milliliters, that's also fine too. So these are the volume of the stock solution that is needed. And so what I would do with this number is I would, step 1, add that amount that we just got. And what the solution is. So I'm going to add that amount to my 1 liter volumetric flask. And then I'm going to add water to the fill line. and then mix well. And of course, enjoy. All right, so that's how we dilute. So we solved and got this number. I said this number. There we go. And there's our directions. Add that volume of 14 molar HCl to a 1 liter flask, fill it to the mark with water, and mix well. Just like we said. Any questions, let me know. I'm going to give you 2 more to do. The first problem does not actually have you solve for the same thing. The second problem does. The second problem is what we've been doing. But the first problem asks you something different. To what volume would you dilute a 0.2 liter or 0.2 liters of 15 molar sodium hydroxide to get 3 molar sodium hydroxide? So you're solving for a different term in the first problem. So just be mindful of that. But the formula is exactly the same. Set up your little grid, figure out where the numbers go, and solve for that to answer the question. And then for the second problem, that's what we've been doing. Except it's not asking you to prepare the solution. It's just asking you, what volume do you need of the stock solution? So solve for the stock volume there. Okay, so try these 2 problems. You're not preparing solutions, so you do not need to give me directions. You just need to give me the answer to the problem. And again, the trick is setting up your information in a way that you can identify what's in the problem and put it into this grid. Okay? And if the grid isn't helping you, make a list. Either way works, as long as you organize the information. So do that, solve the 2 problems, type your answer in the chat here, and we'll go over the answers in about 5 minutes. See you in a bit. All right, 1 or 2 more minutes and we'll go over the answers here. All right, so there's our first problem. And I gotta find the stylus. There it is. Okay, so for this first problem, my stock solution is 15 moles per liter because it's the bigger one. And my diluted one would be 3 moles per liter. Now I gotta figure out where this volume goes. 0.200 liters of a 15 molar solution. So this is the stock solution. And I need to dilute this to some volume. So how much solution will I have when the dilution makes the solution 3 moles per liter? And so that's this. So I have to solve for it. So I'm solving for this one, which means that I'm going to rearrange my expression to look like that. And so that's going to be stock molarity is 15 moles per liter. Forgot my dot in there. That's okay. The volume of it is 0.2 liters. And the dilute molarity is 3 moles per liter. Those cancel. And so I get 15 over 3 is 5 times 0.2 is 1 liter. So if I add enough water for my 0.2 liter 15 molar solution to become 1 liter, so roughly 800 milliliters, but volumes don't add, it turns out. So add enough water until you have 1 liter. You will then have a 3 molar solution. All right. And then what volume of 6 molar sodium nitrate is needed to prepare this many liters of 1.2 molar sodium nitrate? So again, set up the grid just like you did before. So here's my stock solution, because it's the greater concentration. And I want this to be my dilute volume, or molarity. And I want this much of it. And so I got to solve for that. You'll notice I write down the formula every time, identify what I need, and then solve for it. Because you should always just be doing the algebra. Like, it takes 2 seconds to do that, and I know I'm doing it right. Don't memorize formulas. Like, if you memorize this formula, that's fine, but don't memorize the second part. Derive it. It will save you brain space, especially as you get older and you realize that you need that brain space for other things, like people's names and their birth dates. So dilute molarity is 1.20 moles per liter, and the dilute volume is that. And then my stock molarity is that. I'm not even going to try and pretend that I can do that math in my head. 1.2 times 0.525 divided by 6. 0.105. So if I take 0.105 liters or 105 milliliters of stock solution and dilute it to a final volume of 0.525 liters or 525 milliliters, the molarity of the solution will be 1.20 moles per liter. All right. That's how we do dilutions. Any questions, let me know. All right. We have about 10 minutes, and that's enough time for me to do one practice problem or so in the next section. So we'll do that, and we'll do the rest of them tomorrow when we go over the lab, because the lab is basically what we're doing. Oops, I clicked on the wrong window. There we go. The lab is basically what this section is. It involves an activity called titration, which involves molarity. So we're going to do all this, and then we'll do large parts of the lab tomorrow so that you can see it. Titration and stoichiometry and molarity go together hand in hand. This is one of the most common applications in the laboratory. You're going to be doing a lot of this in 161 and 162, particularly if you have an in-person lab. I don't actually know what they're doing next quarter for in-person labs. I think Valerie is not doing them, but I'm not sure. But we are starting to try and go back to them. I am teaching my first in-person lab I'm doing 163 in the spring, and they have in-person labs, and I was like, oh, sweet, that's cool. And nobody's going to have used a beaker before, so I'm going to be like, that's going to be a lot of fun. Okay. Anyway, let's talk a little bit about some experimental stuff that you could do in the lab. So now that you have seen concentration, and you know how moles per liter is expressed, we can use those in stoichiometry calculations. Remember that chart that we had? I can turn moles and volume back and forth using concentration, because remember that MV equals moles. So if I multiply the volume by the concentration M, I get moles. And if I know the number of moles of something, I can do a chemical reaction with it and do the calculation, right? So that means that this chart that we had before now has these parts on it that we can add in to ask other questions. So let's do one in the last 10 minutes here, and then we'll call it a night. And we'll do the other ones tomorrow before we talk about the lab. So let's do the first example here. Let's suppose that I give you this reaction. And you'll notice that these are aqueous, which means that they can be expressed in either grams of the solid that I put in, or I could express it as a molarity. I could have a certain amount per liter. And so for the first problem I'm going to give you, I want to know what volume of this molarity of solution will react completely with 4.9 grams of phosphoric acid. Now, because I am solving for a volume, that means I'm going to end on a volume. So I'm going to end here. And I gave you a mass to start. So you're going to turn grams of H3PO4 into, we'll just follow the chart, grams into moles. And then we'll turn moles of phosphoric acid into moles of the other thing, which would be sodium hydroxide. We'll use these coefficients to do that. And since I know the number of moles and I know its molarity, I can turn it into a volume. So let's do one of those problems. so you can see that in action. I just have to clear the PowerPoint or the Photoshop real quick. So we'll do that. We'll put that on the screen. All right, and let me write out our little blueprint over here. So we had grams of phosphoric acid, which we're going to turn into moles. Oops. There we go. All right, so let's write out the calculation here. So I have 4.90 grams of H3PO4. I messed that up. All right, and then I can turn grams of phosphoric acid into moles of phosphoric acid. And those would cancel out. How do I get grams per mole? You know how to do that by now. Go to LenTech. Look up the molar mass of grams per mole. We'll do that in a second. Let's do this part next. I'm going to move all this out of the way here real quick. Hold on. Out of the way. Oops. I clicked a few times and it got angry at me. How do I do this step? We use the balanced chemical equation to fill in the numbers. And then we'll do this. So now I need to turn this into a volume. How do I turn moles of something into liters? Well, this just looks like molarity, but upside down, right? And let's see how that works out. So if I know the number of moles of something and I divide by the molarity, which is expressed in moles per liter, what do I get as a result? Remember that if you are dividing by a fraction, that's like multiplying by the reciprocal, right? Which looks like that. And then these would cancel. So this is just my molarity on the division side. So it's like dividing by molarity. All right, so let's go fill in all these numbers. So first of all, we'll go to LenTech here. And let me get LenTech on the screen for you. So we'll look up H3PO4, so H3PO4. And it weighs 98 grams per mole, so we'll put that in our calculation here. So, oh, we'll do it in black, though. So 98 grams per mole. Next, we need the balanced chemical equation for how many moles of phosphoric acid and how many moles of sodium hydroxide. Well, what coefficient is in front of H3PO4? It's a 1. And what's in front of sodium hydroxide? It's a 3. I need 3 of the top thing to react with 1 of the bottom thing. And then finally, how many moles of sodium hydroxide are there per liter? Well, according to the problem statement, there are 0.250 moles of sodium hydroxide per liter. Because the number that I wrote here, this is the same as this, right? Which is the same as if I just did that. And 0.250 is the same as 0.250 divided by 1, right? So I'm just going to stick a 1 in that blank. You don't have to put a 1 in that blank. But if it makes you feel comfortable, go ahead and do it. All right. Finally, I can just multiply all the numbers together that are on the screen. 4.9 times 1 times 3 times 1 divided by parentheses 98 times 1 times 0.250. And the answer that I get is 0.600 liters. So, what volume of 0.250 molar sodium hydroxide would react completely with 4.90 grams of phosphoric acid? I would need 600 milliliters, or 0.600 liters. Which is a lot. That is a lot. But that's the answer that we get. All right, so that was one example. I have another example that I'll do tomorrow, and then some practice problems. I don't want to do the 2 examples and then just turn you loose on them tomorrow, because we only have like 1 or 2 minutes left in the class anyway. So we'll stop here for now. And when we pick up tomorrow to talk about the lab, we're going to do these last few problems that are on these slides here. So this problem here we'll do, and then we'll do these problems here. Oops, we're not done yet, so we're not going to do that. And so we'll do all this tomorrow. So I'll just flip this back to here so that it bookmarks this is where we were. And that's it. Yep, so I do want to thank everybody for coming out to the lecture. This was the last lecture. We're going to do a little tiny bit of tomorrow during the review Q&A. But we're basically done. Like, this problem that I showed you is the last thing that we learn. So, and it's complex, and it's important, and it's kind of obnoxious that it shows up at the very end. But do make sure that you understand how to do those types of problems, because you're going to see a lot of them in 161 labs. And we're going to do that even more in 162. So, yeah, that's all I have. Thanks for coming out to the lecture. Make sure you get quiz number 8 in tonight, because it'll close. There's an exam on Friday. Last review stuff tomorrow. See you then.